Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Well, we've been going through the Milky Way and talking about it, and we've gone through a lot of properties of the appearance and the naming of aspects of the Milky Way. But now let's actually look at how the Milky Way evolves and is formed over time. So galaxies have to come from somewhere. And so let's look at what we have on these things. And here's kind of a nice little summary of things that we look at as properties of the Milky Way that must be part of it. And so we can look at remember the Milky Way itself is a spiral galaxy. It's got a disk, it's got a halo, and it's got a galactic bulge. And the disk is really flat. It's got young and old stars. It's gas and dust. There's star formation. Stars are moving in circular orbits and there's spiral arms. And overall, it's got blue spiral arms, and the colors of the stars are kind of whitish because you've got a mix of red and blue type stars. Now in the galactic halo, the halo is pretty spherical. Maybe it might be flattened a little bit just because, pull at the top. There are really only old stars contained in globular clusters, and those are the only things that you have in them. There's literally no dust at all and no gas in the galactic halo. And there has been no star formation during the last 10 billion years, as we've seen from the types of stars that we find in population 1 type stars. Actually, population 2 type stars, none has happened in the last 10 billion years. The stars have all sorts of random orbits in the halo. And there's almost there's no substructure. There's just like globular clusters and maybe some tidal streams and things like that, stars being ripped apart, which we'll talk about in a second. And in general, the halo looks pretty red. The bulge itself is a little different. It's kind of a mix of the halo and the disk. It's pretty flat, but it's flattened along the way of the disk. And it contains both young and old stars, but there's many more old stars. And the more stars, the farther away they are from the center, the more old they are. There's lots of gas and dust, but in the inner regions, but that's only in the central region of the Milky Way, which we'll talk about in the future. And there's ongoing star formation in the inner regions only because there is gas and dust happening. But the star formation is only happening in the very, very central regions of the galactic bulge. However, the stars all have pretty much random orbits in the bulge. But there's a net rotation around the galactic center, and there's always near a ring of gas and dust near the center in the galactic nucleus, which we haven't talked about yet, but we're going to soon. And the galactic bulge tends to look yellow-whitish because of the presence of older stars. All right, so this is kind of our general picture of stars in the picture of the Milky Way. We've got old stars in the halo. Globular clusters are distinctly old. The O and B type stars are only found in the disk. There's emission nebulae, which are those hydrogen gas clouds, which are pinkish. The sun is about 8 kiloparsecs, or about 30,000 light years from the center. The galactic bulge is a mix of old and young, and in the disk there's only young stars, but you can find that there's a lot of old stars too, but you will only find the youngest stars in the disk, in the disk area. And there's the gas and dust is predominantly in the disk. And open clusters are blue and white types things like the Hyades and the Pleiades, and the double cluster in Hercules. Those things, not in Hercules, in Perseus. That's what's found in the disk. The globular clusters such as M3 and M13, those are found in the halo. All right, so how did the Milky Way form and create this structure? Well, in a very, 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 very general sense, take small bundles of gas and dust in little dwarf galaxies and then smash them together. They have, on average, as they collide and form a larger ball of gas and dust, they will in general have some sort of generic rotation to them. And as they collapse together, they will have there will be some orientation that will have a general rotation to the whole thing that is the average of all of their angular momenta that is averaged over the entire thing. And it will flatten along the axis of that average rotation to make a disk. Once it does so, matter can then, the gas and dust can then fall into the disk, because that's now where most of the matter is. And as then the mass starts to spin up because material starts to fall into the plane, and eventually you get something where you have a bunch of things that kind of pass through the disk, and those are the old stars in the halo. And the disk then is ordered because that was where the gas came from. So the rotation initially was a big globby sort of spherical thing, but that got flattened, and then the gas kind of just fell straight down, whereas the stars that were formed from the original group were already formed, so they're just going to keep their random motion. So that's what the yellow dots are. The yellow dots are the old stars that were formed before the formation of the galaxy or during the formation of the galaxy and before the gas was formed. And in fact, not before the gas was formed, but out of that gas. And the gas that was there was almost all hydrogen and helium. And so those stars were formed out of gas that was only hydrogen and helium. And that's what we mean by metal poor. And so this concept was actually come up with by Laplace in terms of his idea about the formation of the solar system as well as the formation of the galaxy. So we get the disk being a gaseous component because the gas will collapse on the away along the axis of rotation. But the halo, which is stars, won't do that sort of collapse. They'll just kind of randomly buzz around each other, and they will stay buzzing for a very long time. And they've buzzed for billions of years, so they're going to keep going like that. So in general, we take small dwarf galaxies that have very young stars in them, say 10 billion years ago. Over 10 billion years ago, those young stars became the globular clusters that we see in box A. And those globular clusters were made from stars that had almost no gas, almost no dust. They had almost no carbon, no nitrogen, no oxygen, no iron, almost nothing, almost made purely of hydrogen and helium. And so that early generation of stars, that first generation of stars, were created the globular clusters, and that's what the yellow dots indicate. And so those stars, some of them were O and B type stars. Of course they were. They died though, and they seeded the first sets of stars that then became the next generation, and that material went out into the gaseous component, which then collapsed along the axis of rotation to keep the gas going. And the gas was not completely used up in the first sets of stars formed as the small dwarf galaxies merged. All right, so that's how the Milky Way was probably formed in the most general sense. And so we still have little galaxies around us, like the Ursa Minor Dwarf, the Sextans Dwarf, the Carina Dwarf, the large and small Magellanic Clouds. All these little tiny dwarf galaxies still kind of hover around the Milky Way. And so they're orbiting the Milky Way. They're still there, but they could get absorbed. And in fact, gravity does work. So they orbit, which means they'll eventually lose some of their angular momentum and merge with the Milky Way. But wait a second, there's that Andromeda Galaxy thing. It's the same mass roughly as the Milky Way. Maybe it's bigger. And that means that the Milky Way and Andromeda are probably falling towards each other. That's really interesting, but let's talk about that in a little bit. So we can have evidence for this concept of dwarf galaxies getting stripped apart by our galaxy, because there seems to be streams of stars that if we look at certain areas of the sky, we find that there's streams of older population 1 type stars, meaning metal poor population 1 types, or on the metal poor end of population 1. And these are little galaxies that have been tidally stripped apart. And as they get stripped apart, they get stretched into where you can't even see them anymore. And so the Spitzer Space Telescope was able to use infrared view to actually find these stellar streams that orbit our Milky Way. And these stellar streams are thought to be the remnants of dwarf galaxies that have collided with our Milky Way. And in fact, the large and small Magellanic Clouds are in the process of merging with the Milky Way, and dynamically they will merge with the Milky Way in the future. And we have evidence for these star streams, and specifically this is an amazing picture from Astronomy Picture of the Day back in 2008, specifically June 19th of 2008, and this comes from Blackbird Observatory by Dr. Gabani, and it also he collaborated with a number of people in order to show the tidal streams around this particular galaxy. These tidal streams demonstrate quite clearly that little dwarf galaxies do get ripped apart by bigger galaxies, and Essentially, they lose their cohesion because the bigger galaxy simply stretches out these little galaxies, and the stars become streams rather than these clots like little dwarf galaxies or spirals or something like that. And eventually, the stellar streams merge with the rest of the galaxy or become part of the halo component of that galaxy. But they don't have enough gravitational influence in order to tear apart the spiral structure of that larger galaxy. So they just kind of orbit in their streams. And so they're kind of like stellar streams that are similar to meteor showers that the Earth encounters as a comet breaks up. They just kind of orbits through the galaxy plane. All right, so we can then make a thing. We can think that if we look at extremely deep photographic surveys of looking far, far, far away, and therefore far, far, far back in time, we see a gallery of Milky Way-like galaxies from long ago until today. And if we think about the most ancient things, we'd say, well, if we have little tiny dwarf galaxies, those little tiny dwarf galaxies will be very, very blue because, well, they're mostly hydrogen and helium, so they'll be producing lots of blue stars. And that's what we think about with the 11.3 billion years ago. It would be two little galaxies all merging together. So it would be blue, tiny, misshapen, and bright. A billion years later, those things merge together to form something a little bigger. And if another half a billion years later, that'll merge with something else. And then another billion years or so later, that'll merge with more things and acquire more dust and gas. And then another 3 billion years passes and it merges with yet still more. So a continual merger of small dwarf galaxies appears to be the dynamical way that Milky Ways form, like grand spirals form. They keep getting resupplied with more gas and more dust by colliding with more little dwarf galaxies that are primarily gas and dust. So they enrich the spiral structure with more material to create more stars. And so we can see that maybe 3 billion years ago, the Milky Way was a little bit smaller, and another dwarf spiral kind of collided with it to form more Milky Way stars. So this is a kind of photographic support for the idea of the formation of the Milky Way by looking at the most ancient galaxies that are very, very deep in space and very, very far back in time, therefore, because it takes time for light to get here from there. So we see things as they were ago if we look farther back in time. And then it really only begs the question, how the heck do we know that it's that far back in time and that far away? And that we'll get to. Have no fear, we will get to that. So what we do is we find that things that are farther away are misshapen, tiny, and bright. And as we get closer and closer, and with almost no spiral structure, and it takes only until later, much later, that you can get a structure that's large enough, that where enough stars have gone through enough generations, you've created enough dust to actually get things that look like dusty bands, such as we see in the lower right image, where there's little dark dusty bands that are just barely, barely, barely visible. And this is a NASA image, and I believe this is a Hubble type image. So yeah, I'll definitely provide the links on the YouTube channel for it. In any event, this is a good little simulation that I think was put together by Dr. Summers at the Space Telescope Science Institute to try to show what would happen as the Milky Way is eventually going to collide with the Andromeda Galaxy. So in about 5 billion years from today, the Milky Way and the Andromeda Galaxy will collide. They will merge because they're the two big bad boys in the neighborhood. And eventually they will meet and form one big galaxy that we call Milkomeda. Why? Because Milky Way and Andromeda Galaxy. So Milkomeda will be the name of the big galaxy. Notice when they merge, the tidal disruption happens and stars are flung out, and the colors go from blue to red. And the reason colors are going from blue to red as the cores merge is that star formation is occurring as the gas clouds merge and do wild outbursts of star formation and get rid of all the gas and form all these stars in massive amounts all at once. And then the spiral structure is destroyed and you're left with just a bunch of old yellow stars and no gas or dust as it was burned up in a huge, huge, huge event. And that's what's going to happen in about 8 billion years from today. 8 billion. Not in 100 years, not 1,000, not 10,000, Not 100,000, not a million, not 10 million, not 100 million, but not even 1 billion. 8 billion years. That's in more time in the future. That's twice as long in the future as the Earth has been alive. All right, so what would it look like from Earth? What would that whole simulation look like? So here's what it looks like if we look towards the towards the Andromeda Galaxy today. We see the Milky Way in the foreground is kind of, we're pretending the Earth will survive this long, and you can actually set up a camera. And you can pass this down generation upon generation and take the same image over and over. But hey, we're making a simulation here. So this is all simulated at this point. So the Milky Way in the sky, Andromeda there. And then we jump ahead about 2 billion years. The Andromeda Galaxy is now so large in the sky that it's something that everybody will always notice and will be part of their lives if there's people on the Earth in 2 billion years from today. Maybe the giant cucarachas that are going to be surviving will enjoy it, the view. All right, so then we go to about 3.5 billion years. The Andromeda Galaxy is now extraordinarily large in the field of view. It takes up about half the sky, more than half the sky in our view. And then approximately very soon thereafter, the stars, because they're starting to collide, there's all sorts of pink star formation regions as stars are formed in furious amounts. There will be supernovae in the sky, tons and tons of super large Orion nebulas and Trifid nebulas. The sky will glow pink at night from the hydrogen glow in the sky, and multiple stars will be going supernova in the night sky. And then if we go just a little bit further, the star formation continues even more robustly, and large superclusters of stars will occur, and there will be massive amounts of star formation that will disrupt and destroy the remaining gas in the Milky Way-Andromeda system, as it's a race between eating up all the gas and expelling it out into space in huge stellar winds that we saw from the Orion Nebula. So massive stars can cause huge stellar winds, which will blow the gas away. And in fact, as these supernova explosions occur, the star formation will dissipate rapidly because the gas is light and doesn't do well against massive shocks. And so maybe in about 4 billion years, as they pass by each other, the Andromeda Galaxy will be all tidally stretched. Most of its gas will be used up. It'll all be red stars then. There will be no O and B type stars, but it'll be an interesting and beautiful view. Very strange and red in the sky. And then in about 5 billion years, the core of the Milky Way and Andromeda will appear as a pair of bright lobes in the sky in some direction. That will be just the core remnants of that, and there will be some residual star formation, but really it'll be these two sorts of wild glows in the sky. And then after about 7 billion years, there will be a massive elliptical galaxy. The bright core dominates the night sky. In fact, it might be so bright that there would be absolutely nothing to see at night. There would be very few stars unless both the sun were down and the stars. But in 7 billion years, the sun's not going to even be here. And likely the Earth will be burned to a cinder by the sun becoming a red giant. But hey, maybe this has been taken on one of the distant moons surrounding Saturn that survived the growth of the sun to a red giant. And so this particular sequence was made by the NASA group at Space Telescope Science Institute with LeVay and Van der Merel and Hollis and Mellinger. And they basically put this together to kind of show what the sky would look like from that wonderful, wonderful image that we now know when the Milky Way will collide in about 5 billion years with the Andromeda Galaxy. So I have some questions for you to go over and to think about, and we can actually ask what the heck is going on. But we have all this interesting evidence that the Milky Way evolves from an early state from photographic evidence by looking at ancient galaxies deep in the past, that most galaxies were small and blue and misshapen and bright, and then as time progresses, those blue misshapen galaxies that were just deep in the past were mostly made of hydrogen and helium, and then as time progressed, the stars, generation upon generation upon generation, made more and more dusty material like carbon, nitrogen, oxygen, iron, magnesium, and all the other elements that form the dark, dusty bands that would eventually end up to become planets and other stars. So we have kind of a theory about how the Milky Way formed and where it came from. So we'll talk more about the Milky Way next time. See you soon.